So these are all kind of the alternate examples from the textbook. So let's just kind of go through each of those, and hopefully that'll give us a good idea of what's going on with this whole thing. So we're going back to confidence intervals, right? So that's the big thing that we're stepping into. So we're back to confidence intervals. And hopefully you guys had a chance to watch the one video. But the big difference is now that we're doing confidence intervals and we're talking about quantitative data, right? All right, so we're doing quantitative data, maybe data. All right, and so remember when we start talking about quantitative data, we're talking about numbers like 1, 2, 3, 5, 3, right? 2, whatever, and we're gonna start talking about averages. So we're talking about sample means, and our whole goal, right, is to try to figure out these population means. So that's what we're trying to do, and we're trying to figure out mu, right, our population mean. And so basically, if you watch the video, you saw that we started to come to this new idea, right? We want to do this. We want to take x bar plus or minus z star, our critical value, sigma over the square root of n. So that's what we want to be able to do. The problem is that we can't really do that because we don't know this population standard deviation. So this thing is missing, right? How far does the data actually spread out from the population? So when we lose that value, we replace that with this S, right? And so S is the standard deviation of the sample. So we replace that with S, but the problem is as soon as we do that, this formula no longer worked. Our capture rate wasn't very good. So we now come to this whole new formula called a t distribution. So x bar plus or minus t star s over the square root of n. And this is going to really be our formula for a confidence interval for a mean, all right? So the first thing that we look at when we need to do these confidence intervals, just like we did before, is we have to figure out how far out do we have to reach from my x bar, right? How far out do I have to go in order to capture like 95% or whatever? And what you would have seen from the video is that it's a little bit different. So we now come to this new distribution called the t distribution. Now, do you guys all have access to that t distribution file?
I think so.
Okay. So let's say that we want to make a 98% confidence interval for a random sample of 20 observations. So the first thing that matters is how many observations that I have. And you might say, why does that really matter? And the reason that it matters is because S does a better job of estimating sigma as n gets bigger. Let me just pause here real fast, guys. Do you understand the difference between S and sigma? Yes, no, maybe? Okay, so nobody's saying anything. So I'm going to assume you don't know the difference between S and sigma. So imagine that at Cosby, right? I was able to take everybody from our AP stat. And let's say we were able to take the temperature. You know, I have like 50 students in AP statistics. Okay. So if I was able to take everybody's body temperature and everybody was healthy, right, which is the big question at this point, there would be 50 dots here. Do you guys understand that idea?
Yeah.
There would be some distance away that each value would fall away from mu, the population mean. So there would be some distance away, and that typical distance away would be sigma, okay? Now let's say that I only randomly select 20 of my students instead of everybody. Well, now how many dots do I have? Only 20, right? And how far are these dots away from the sample mean? That would be S, okay? So sigma's talking about everyone, where S is talking about our sample of people. And here's the deal. We would hope that S would be the exact same thing as sigma, but it is not. Usually it's too small, okay? And think about it. If I only picked 5 people from the population, you could get 5 people that were really close together, and then S would be really small. Or you could get 5 people that are far apart, and S would be pretty big, but typically you'd see that it would tend to be smaller than what sigma would be. And that's the problem. So it's not doing a good job. S is not doing a good job of estimating sigma. So, and it does a worse of a job right? Think about it. If I have 50 people here and I only pick 5, that's not going to do as good of a job as 50 people and I choose 40 of them, right? The 40 would be much closer. So this t distribution is going to depend on my number of observations. But the first thing that we do is we change that to what we call degrees of freedom. And you might say, well, why the heck do we do that? Well, because it's going to change here soon. All right. Hey, I'm just going to mute all of you guys for a second. I'm just getting a little feedback, okay? All right. So the first thing that we do is we grab our degrees of freedom, which is simply your sample size minus 1. So in this case, my degrees of freedom would be 19. All right. So then what I need to do is I then go and I take a look at my t distribution and I go find 19 degrees of freedom, which is right here. You can see that right there. And I need my confidence level, which in this case was 98%. So I find the matchup of these two columns, and I can draw right on here. So I find the matchup of these two columns, so 98% confidence. Okay, oops. There it is. Oh, man. Okay, so 98% confidence, 19 degrees of freedom, and we can see that my critical value is 2.539. So that's how far I would have to reach out to get 98% of the values, okay? So that's my T star value, all right? So T star, and I need to clear that, is 2.539. Now we want to look at a couple of things, 2.539. We want to look at a couple of things. We want to say, okay, first of all, how does that compare with Z? Right, Z star. Well, if I actually go back and look at the same table, on the very bottom is Z star, where it says infinity. And that value is 2.326. So what do you notice? First of all, we notice that T star is wider. And if you go back and watch the video, you'd see that the T value is always going to be bigger than the Z. So basically what I have to do is I have to reach out farther to grab 98% of the values because of this whole problem with estimating sigma with S. All right. Okay, letter B, a 90% confidence interval based on a random sample of 95. All right, well, my degrees of freedom in this case would be 95 minus 1, which would be 94. And then I go look at my table. And now what you'd see is 94 is not on this table. All right, so you'd see it. So we have to take a pick. So we either have to go with 80 or 100. And what we always do is we always round down because we want to reach out further. Notice how it's bigger at 80 than it is at 100. So we'd go 90% confidence, and we'd go down to 80 and be 1.664. And that would be our best guess for what it could be. So T star would be 1.664. Now, again, we ask ourselves, how would that compare to Z star? Well, Z star is 1.645. So what do you notice about these two this time? They're actually pretty close, right? Do you understand that? They're pretty close to each other. They're a lot closer than they were in the previous example. And the question is why? Well, because when you take 95 values, S does a pretty good job at estimating sigma. Okay, so that's that point there. Okay, all right, let's keep moving on. Let me just unmute you guys and ask if you have any questions about that first. So do you guys have any questions about that first?
No.
No? Okay, it makes sense so far?
Yeah.
Yes.
Okay, all right, then let's keep moving on. Okay, so then the next part is we're going to go and take a look. So what conditions do we need in order to use this T distribution? All right, so what were our conditions before with proportions, right? With proportions, we had 3 conditions, right? So just remember that. We needed random samples, we needed the 10% rule, and we needed the large counts rule. That's what we needed before. All right, with T, it's a little bit different. We have 3 conditions again that we're going to use. We're going to use the random sample, we're going to use the 10% rule, and then the third one is going to be either our normal or large sample size condition. So that says one of 2 things. Number 1, the population is normal. Okay, and we can determine that either if they tell us or if we graph the data. And that's what's going to be new here. We're going to be able to graph the data. Or n is at least 30. So those are my 2 conditions, okay? Now, when I graph the data, we want to make sure that there's no strong skewness or outliers. All right, so let's go ahead and take a look. So let's look at this first one. A, we want to estimate the average time in minutes in order to receive regular coffee at a local coffee shop. So the times for 5 randomly selected visits are shown in the dot plot. So here you go. Everybody take a look at this. So first of all, did they tell us it was normal? No. Is my sample size big? No. So then I look at the graph, and what do you all notice about the shape of this graph? It's skewed to the right with an outlier. Do you see that? So here's the question. Does that look like it comes from a normal population? And the answer is no, right? So we can't use the t-distribution here because the data shows skewness and an outlier. And n is small also. So because n is small. Now, if n was big, it wouldn't matter what it looked like. So we'd be able to use it, all right? So I would not be able to use the t-distribution. My conditions would not be met, all right? All right, letter B. We want to estimate the average height of high school students. The box plot shows the distribution for 100 randomly selected. Could I use the t-distribution? So does this fit the normality? Not really, but does it fit the large sample size? You got it. So 100 is greater than 30, so we have a large sample size. So we can use the t-distribution. And really what this has to do is central limit theorem kicking back around, right? All right, and the last one, letter C. A middle school counselor wants to estimate how many minutes on average students spend doing homework. So a histogram shows the amount of time a random sample of 20 students spent doing homework. So let's take a look at this. So first of all, sample size is small. Does it show any deviations from symmetric, right? Doesn't this look symmetric and mound shaped? Yeah, so we'd be totally fine to use it. So yes, we can use a t-distribution. Why? The data doesn't show strong skewness or outliers. So we're good to go. All right. So there's our conditions. Okay. So people always have questions about this. Let me unmute you guys and see if you have any questions. All right. Any questions on that?
No.
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 All right. Pretty easy, right?
Yeah.
The one thing that you guys have to remember is that you're going to have to come back and graph the data. So if they give you the data on your paper, I'm going to expect to see a graph. Okay, does that make sense?
Yeah.
All right, so you're going to have to graph it, and then you're going to have to kind of have that same conversation like we're having here. Now, in the other video, I made a normal probability plot, which is just great, because if it shows the linear pattern, then you know it's approximately normal, so you're good to go. All right, let's keep moving forward then. All right, so on to the next one. So now we're going to do our whole one sample t-interval for mu. All right, so Reese believes that students in her large high school spend way too much on their phones and other devices. To investigate, she estimates the mean amount of daily screen time for all. So the students in her school by taking a random sample of 50. All right, so we got that first. So n is 50. She finds an average daily screen time for the members is 7.1 with a standard deviation of 2.4. Now notice, do you see how they gave us S? That's the standard deviation of these 50 people. And as soon as I have S, I start thinking T distribution. Okay, so as soon as I have that, I start thinking T. Okay, construct and interpret a 90% confidence interval for the mean time, daily time for all students of the school. All right, so let's go ahead and do this. So this is obviously a confidence interval. So it's asking us to go through all of the steps of panic just like before. All right, so let's go ahead and start off with this. So my parameter of interest is now mu, right? We're interested in this right here, mu, the mean amount of daily screen time for all students at the school. Of daily screen time for all the students in this school. Okay, so we're starting off there, easy peasy. Now before, right, it was always, before we were always dealing with P, the true proportion, but now we're talking about quantitative data. So we're back talking about means, all right? Okay, next thing. So now we need to assess our conditions. Okay, same first two are just so easy, right? So we were told it was a random sample. Easy peasy. We know that there's must be more than 10 times our sample size, 10 times 50, 500 students. All right, so that's easy. Okay, the third one, now this is the new one. So we come back and we talk about our normality / large sample size condition. Okay, large sample size. And what do you all notice about the sample size in this case? And I have you muted, so you can't respond anyways. But the sample size was 100, which constitutes a big sample size. So 100 is greater than 30. So we have a large sample size. And because of that, we can use the t-distribution. That central limit theorem really kicks in. The sampling distribution of the x-bars would be approximately normal. Boom, we're good to go. We have our normality. All right. And now, and again, one of the conditions of using t is you want that population to be normal. So that's kind of the goal as to what we're looking for there. All right, let's go ahead and name this interval. So this is now a new one. It's a one sample, because I have one sample, t interval, t confidence interval. Okay, so we got a one sample t confidence interval. And anytime I write t, I'm also going to throw in the degrees of freedom. So in this case, my degrees of freedom would be 100 minus 1, which is 99. All right, so let's go ahead and get our interval. So it's going to look like this. X bar, my sample mean, that's my point estimate, plus or minus t star, that's my critical value, s over the square root of n. I want this to be sigma, but I don't know the standard deviation of the population. So I replace it with s, and when I replace sigma with s, that's where the t distribution comes in. Well, now this is all pretty easy. 7.1 is my x bar, that's my point estimate. Okay, I need my critical value. So I need to go to my t distribution sheet. So I have 90% confidence. My degrees of freedom was 99. Now, even though it was 99, I still have to back all the way down and go down to 80 because that's the next closest one. So you always round down in the table. So it'd be 1.664. And it'd be S, which is 2.4 over the square root of 100. Now just be careful, that's n there. So a lot of times I see people make mistakes with that. Okay, I can go and run this in the calculator as well. And so let's just show you what that would look like. Menu, stat, confidence interval, and we can see a t interval right there, okay? Now it's gonna ask you, do you have data or stats? Now in this case, we only have the stats. We have the mean and the standard deviation. So stats, X bar was 7.1, S was 2.4, N was 100, and the confidence level was 90. And again, you guys, I'm recording this, I'll put this on the classroom, but hopefully you guys are just following along with this. And we hit okay. And there's my interval, 6.7 to 7.5. So 6.7 to 7.5. 6.7, 7.5. Okay, and now what do we come back for our conclusion? So now we come back and we do the same thing just like before. We're 90% confident. It's a big font. Let me make that smaller. So we're 90% confident. Oops, if I could get the numbers. Percent confident. The interval 6.7 to 7.5 captures the true mean amount of daily screen time for all students in this school. And there we go. I would be interested to see what screen time is like if it was 6.7 to 7.5 hours before, what it's like now that everybody's got all this extra time at home. All right. So let me unpause you guys, see if you have any questions on that. So any questions?
No.
No.
No? Seem pretty easy?
Yeah, it's pretty similar to other panic.
Yeah, exactly. It should be the exact same thing. And the nice part is you guys don't have to learn anything more, you know, interpreting what's it mean to be 90% confident. The exact same thing as before. 90% of all the possible intervals will succeed in capturing mu this time. So, you know, you really don't have anything else that you have to add in. Now, you guys might not have calculators at home. And if you don't, you can go to the Rossmann Chance website and go to the theory-based inference down here. And if you do that, you go to one mean, you would put in the data. So you'd put in 100, 7.1, 2.4, and you click calculate. And when you're there, then you just go over here and you click confidence interval and you change it to 90 and calculate confidence interval, and there you go. All right, you see how that works out pretty nice? All right. Okay, so there's one of those. So I assume they're all good. Now it does ask in part B, it says a recent report states that US teens have 6.78 hours of daily screen time on average. Does this interval provide convincing evidence that the mean differs from 6.7? Let me go look at our exact interval again. It was 6.701, right? I kind of rounded. So it's 6.701. So what do you notice about that? Does 6.7 actually fall in that interval? And the answer is no, right? So 6.7 does not fall in that interval. So therefore, it gives us evidence against that claim being true. In the interval, so it gives us evidence against this being true. There you go. All right. Okay, so let's move on to the next one. So I think we got like one more here. This one's going to give us all the data, so it gives us a chance to run through everything. All right. Okay. So the GOAT, so the greatest of all time. So many people think Michael Jordan is the greatest basketball player of all time with a career scoring average of 30.1 points per game. Some curious statistics students wonder about his scoring average for all of his home games. So they take a random sample of 15 games from Michael Jordan's career. Here are the number of points in each of those games. So construct and interpret a 95% confidence interval for the mean number of points mu that Michael Jordan scored in all of his home games. Okay, so first thing we have to understand is what type of data is this? And the answer is quantitative, right? Which as soon as I know that it's quantitative, we're talking about means. All right, guys, we just got to use our brains here too. Notice here that it says the word mean, right? So should you have anything with proportions? And the obvious answer is no, right? There should be absolutely nothing with proportions here. All right, as soon as I see the words means, I ask myself, do I know sigma, the population standard deviation? Did they give it to us up here? No. So I replace sigma with S, and that's where this t distribution is coming in, okay? Now, this t distribution never existed with proportions. Proportions is always z, so make sure that you understand that. All right, so let's go ahead and start off with this thing. So we're asking us to do a confidence interval, so we'll go through panic. So mu is, again, I'm just going to copy this. The true mean number of points, MJ scored. Hey, big deal today, right? Tom Brady leaving the Patriots. So MJ scored in all of his home games. Now we're trying to figure this out from these 15 games. Now, realistically, guys, couldn't we just go look at the data of every game? Probably, right? So this is kind of silly, but you know, it's still worthwhile. Okay, let's assess our conditions. Okay, they told us it was a random sample of games. So we're good there. Okay, number two, again, 10% rule, more than 10 times 15, 150 games. I mean, they play like 40 games a season. Michael Jordan played for a long time. So we're good there. All right, third condition is now I need my normality / large sample size. Okay, so do I have a large sample size? Nope, n is only 15. So now I need to go graph the data and figure out whether it could be approximately normal. All right, here's what I'm gonna do. I'm gonna pause my screen. Would one of you mind just reading out all the values for me so I could just type them in quickly? Oops, I don't think I paused my screen. All right, hold on. Okay, 1 second. Okay, pause screen. Can you guys still see it?
Yeah.
All right. Jesse, do you mind just reading them out to me?
Yeah. 35,
Uh-huh.
31,
Yep.
35, 31, 24, 25, 32, 29, 29, 28, 36, 26, 32, 38, 27.
All right. Did you read them across or did you read them down?
Down.
Oh, shoot. No, I'm just messing with you. It's all good. All right. So, okay. So here we go. All right. Resume sharing. Okay. Can you guys see my screen now?
Yeah.
Okay. I'm going to go back to muting you guys. Okay. So now what we need to do is we need to go graph this data. All right. Now, if you're at home, you can go back to that Rossmann Chance site. I'll show you how to do that. But since I have my calculator, I'm going to add a page, number 5. Scroll to the bottom, points, there it is. So here's what we're looking for, everybody, okay, right? It's simple. Do you see any skewness or outliers? And the answer is no. So you're good to use the t-distribution. That's all you have to say. But you do have to show a graph of this. Now, I like a normal probability plot. So I'm going to change my plot type to a normal probability plot. Look, this thing is following a line, right? And if that follows a line, then that means that the data is approximately normal. So that's even better. So I'm going to go ahead and put this one onto the page that we're working on. All right. And let's see if this works. Okay. So I'm going to go ahead, and what you have to do is you have to draw this on your paper. So you have to show this work, whether you do the dot plot or whatever you might do. So the normal probability plot shows a linear pattern. So we can assume the points scored by MJ is approximately normal. Awesome, we're good to go. We want that population to be normal because this looks normal, we're good to go, all right? So again, let's say that you're at home and you don't have a TI Nspire. If you copy those and you go back to Rossmann Chance, one mean, and if you click paste the data, it will let you paste it in, use the data, here's the graph, and look, it's symmetric with no outliers. It gives you the mean, it gives you X bar, S, and then you could change your confidence level over here, and it will adjust everything based off of whatever that you need. So again, this is a great way if you're at home just to stay up to date with the work. The work should not be difficult here. All right, let's go name the interval and finish this thing up. Okay, so naming the interval. So this is means. Again, we don't know sigma, we replace it with S, so it's a one sample t-interval. Okay, formula looks like this. Anytime I put t, I need degrees of freedom. That's a sample size minus 1, which is 14. So x bar plus or minus t star, s over the square root of n. Okay, x bar in this case, I need to go grab it from the work. And actually, honestly, guys, I'm just going to go run it in the calculator, and then it would just come back and fill it in. So I can do that right from here. So menu, stat, confidence interval, t-interval, and this time I have the data. I want to run it on points, and I want a 95. Okay, so here's x bar, and if I scroll down, there's s. So 30.5, s is 4.2. Okay, so 30.5 plus or minus. Okay, I need my t star. Okay, so 14 degrees of freedom, 95% confidence. So I go to my t chart, 95 up to 14 degrees of freedom, and it's 2.145. And again, you'll notice that's bigger than z, right? That's that whole point. So 2.145. S was 4.2 over the square root of 15. And then all my work was in the calculator or in the Rossmann Chance. It was 28.2 to 32.9. So 28.2 to 32.9. And there we go. So we'd come back and just have our conclusion and context. Hey, in this case, we're 95% confident. The interval 28.2 to 32.9 captures the true mean number of points scored by MJ during all of his home games. And that's the big difference, right? We're taking 15 to figure out the whole population. All right, let me unmute you guys, see if you have any questions. All right, so any questions?
So that's why can you hear me?
Yeah.
All right. So for the plot, like, do you have to use the line, or you can just use like the
Like a
like,
dot plot?
yeah, like do you have to use like the linear plot, or you can just like draw the regular one?
Yeah, you can use any plot that you want.
Okay.
All right, so the one I would stay away from, Iverson, is a box plot, okay?
Okay.
But yeah, a dot plot's fair game. Histogram technically is fair game. I mean, the reason I like normal probability plots is because its whole job is to assess normality,
Okay.
right? So like, it does all of your work for you. If these dots fall on that line, then you're free to use the t-distribution. You don't have to talk about anything else.
Okay.
But like all of the rubrics and stuff typically have dot plots, or so you're good to go with all those.
Okay.
What else? Any other questions?
Nope, I'm good.
Okay.
You're good.
All right. So let's do one more, and then I mean I'll leave it open. So that should get you guys through being able to do all of them, right? So there really shouldn't be many questions left, I hope. But the last thing we have to do is figure out sample size. So in this case, a group of students like to estimate the average number of pieces of candy that come in fun-sized packs of Skittles. So they want their estimate to be within one piece of the true mean at 90% confidence. And the standard deviation is about 2.4. So what's the minimum number of packs that they should randomly select to get a satisfactory estimate? So you'll notice that this is a margin of error question. So let's just come back and make sure that we understand our formula. So it's x bar plus or minus t star, and we've got s over the square root of n. So we got s over the square root of n. Now let's just remember our pieces here, right? This beginning part here is my point estimate. This part back here is my margin of error. Now here's the deal. When I talk about this margin of error, in order to use t, I need my sample size. T needs n. What don't I know here? I don't know n. So instead of using this, anytime we do margin of error questions, we just always use z. Okay, so margin of error is going to be at most, we're just going to always use z, and whether it's s or sigma, it's not going to really matter. All right, so we're just going to make our life a little bit easier there. So we want our estimate to be within one piece. So that's my margin of error. We want 90% confidence. So I go grab my critical value, and here's the nice part about your new t-sheet, everybody. It has z at the bottom. So here's 90. Z is the very bottom value, 1.645. So you guys won't ever have to worry about calculating those anymore, unless I give you one that's not on there. Okay, S is, they tell us the standard deviation is 2.4 over the square root of n. Here's my equation, and now I need to go back through and solve this. All right, and so again, depending on your math, it's up to you. First step that you do is divide by 1.645. I got to use a calculator here. So let's see. So 1 divided by 1.645 is 0.607. Now remember, I'm going to round on here, but I'm not going to round in the calculator. Okay, I want to solve for n, so now I multiply both sides by the square root of n. Basically, what you end up doing is you just kind of like flip this whole thing around. Okay, so there we go. And now I divide by 0.608. And then I square both sides. And then I square everything. Okay. Okay, so n would be at least, so 2.4 divided by 0.608. So 2.4 divided by this value. And then I take that whole thing and I square it. And I get 15.58. And remember what you have to do with that. You guys remember? We got to take this number, we always round up. So we need at least 16 packs of M&Ms. Or Skittles, whatever it is. And there we go. All right, and you can always use the n solve or whatever that you need to use for there. All right, so that's margin of error. So let me again, unmute you guys. See if you have any questions on that. So what do you guys think? Any questions on that?
No.
No.
All right. So that's the whole, first topic that you guys have. So anything else you guys would like me to go over with or talk about?
I'm all right.
Good.
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 So, there's some book examples that you guys have to practice. The videos, I picked all the ones that have videos, and hopefully you guys know how to access those videos too for the homework problems.
Yeah.
But I mean, honestly, between the two videos, you probably should be pretty good with being able to figure these out. It's the nice part is it's nothing that's